Okay, welcome back. Any questions or comments? This is where I think we stopped with spin traps. Excuse me. For measuring some free radicals through EPR spectroscopy. We are looking at methods for measuring quantitative measurement of reactive species. We looked at fluorescence methods in some detail because we use them in our lab. We just touched upon the other methods through a list and so on. And then we looked at EPR principle in some detail, and some details on EPR, including the use of spin traps, we have looked at. Any questions, comments on that? You'll also have a chance to refresh your memories and so on and so forth later. But any questions, comments now? Okay, if not, we'll move to the last part of this chapter, which is on biomarkers. Yeah. Oh, it depends on the spin trap. It depends on the spin trap. A few hours is very common. At least yeah, you capture the radicals using a spin trap, and the spin trap is what is analyzed using EPR spectroscopy. In other words, the entire solution. But what the EPR will pick up is the free radical in the spin trap, which has been made into a free radical because it has trapped the hydroxyl radical or the specific radical it is meant for. So if you look at, for example, DPTU, DMPO, DPTU something, DMPO, right? We use DPTU. Strange, I used DPTU more than 40 years ago. Okay, DMPO. DPTU is not a spin trap, and something else, some other chemical, dimethyl pyrrolene oxide or something like that. That's DMPO. That is specific for hydroxyl radicals. So you add it at the time that you want to measure the hydroxyl radicals at that instant, and then in a sample, of course. Then it will react specifically with the hydroxyl radicals and produce a, where is that? Produce a species such as this, or a species such as this with superoxide and so on and so forth, let us say. Okay, so this is what the EPR will catch. So the corresponding spectrum for this is something like this. Although it is specific for hydroxyl. Hydroxyl is 1:2:1, right? But if it has been captured by this, the EPR signal will be contributed by that radical, that electron, as well as the environment of that electron, right? Or there are a lot of nuclei around it, electrons around it, and so on. Electrons doesn't matter, nuclei around it, and so on, right? And therefore everything will contribute to it, and the resulting thing will be this. Only thing is that this is typical. Once you see the spectrum, you know it is, you can associate it with the hydroxyl radical or the spin trapped hydroxyl radical. Yeah, different spin traps are for different reactive species. So this is, it doesn't say which radical it is. Okay, DMPO is definitely for hydroxyl. We have used it for hydroxyl. Some specific for superoxide, some specific for this thing, and so on. It could also cross react sometimes. Then you'll have to be a little careful. You'll get a combined effect. But usually we use specific reactive species. That's not a problem. Any other questions? Okay, then the last part of this chapter, biomarkers, which you might already have some idea of, but you need to clarify your thoughts about biomarkers and so on. Some investigators, especially in medicine, are interested in measuring the outcomes of the interactions of reactive species with the cells or the various biomolecules. Okay, this is trying to understand it at the cellular level and trying to figure out at least the extent of damage for diagnostic purposes. The products of the reactions between the reactive species and biomolecules can be considered as fingerprints of the damage if the following criteria are met. There are known criteria. The first one is that they are unique. The signature must be, the fingerprint must be unique. Not multiple things must give rise to the same fingerprint. They should not be generated by the normal biological processes, only by the disease condition, and they should not originate from the diet that is taken in. If these three are met, then they are a good candidate for a biomarker. Okay. Typical biomarkers are damage to DNA, protein or lipid, which are estimated in various ways in the sample. So, it is pretty much fundamental. You look at the damage extent to the nucleic acid, DNA especially, to the protein or to the lipid, and then that is a good biomarker. The lipid peroxidation, I think I cannot move this, right? So, I will move slightly. Not able to read this at all. Okay. I can read that. Not bad. Okay, the lipid peroxidation is done or is measured. The extent is measured by something called a T-bars assay. Very common assay, well known for people in the field, and in the related field. It is well known. Can you close that? Somebody is coming. Okay. It's well known. T-bar stands for thiobarbituric acid reaction species assay. Okay. So as mentioned, highly popular and quite easy to do, and that's the reason everybody uses it. Right? And it is used as a biomarker of lipid damage in many fields, including food preservation. Remember, we talked about flour damage through milling. It causes damage to the lipid. Even that is measured by T-bars. A lot of lipid peroxidation damages are measured by the T-bars assay and so on. Very popular assay. However, the T-bars has significant limitations in reflecting the realities of lipid peroxidation. This is, if you really want to differentiate finely, then be a little careful about T-bars assay. It will give you a rough estimate, what should I say, a bulked up estimate of the damage. But if you want some fine measurements, then be a little careful. And you can look at your textbook for the complications involved in the interpretations of the T-bars assay. It's essentially you measure, rather you react something and then you measure the product. So, okay, you can look at what the T-bars assay is and things like that if you are interested, just to give you an idea of the biomarkers here. And one of the desired features for a biomarker is that it is easily available, it is easily accessible, or its availability in easily accessible sources such as urine and other bodily fluids, so that the measurement becomes simple. Right? Researchers have used urate oxidation products such as allantoin as a marker of damage. More the damage, more the allantoin levels in urine or wound dialysis, wound fluid or microdialysis fluid, and so on and so forth. This is for urate oxidation. The extent of damage is measured through measuring allantoin, a molecule called allantoin. So, allantoin is a good biomarker or a known biomarker. Good example. Okay. So, that gives you some idea of biomarkers. There are many biomarkers, of course. This gives you some biomarkers of relevance to reactive species damage and things like that in a medical context. Biomarkers are indicators of damage that has already happened. Okay, I am re-emphasizing something that I did in the first chapter, that I mentioned in the first chapter. You should note that the biomarkers are indicators of damage that has already happened. They are certainly good for diagnostic purposes. So much of damage has happened, fine. Okay, but not good for therapeutic purposes because the damage is already done, and since it is reactive species damage, the damage is mostly irreversible. So if you have a huge amount of damage and you're trying to, you need to interpret the damage appropriately and then decide what to do. You cannot relate 1:1 and so on and so forth. Okay, minimum damage, so minimum this thing and so on, so on and so forth. It's a roundabout way of going about it. You need to be careful about it. It's a direct measure of the damage that's already done, most likely irreversible. Okay, we'll finish up with the last video on this chapter. This is, I mean, rather, before we get into the video, any questions on biomarkers and so on? Essentially, the last aspect of it, you need to understand. Not many people do, and be careful about that. Any questions? I asked the others, people who came in a little later. Any questions on measurements, principles, and things like that? Details, of course, you can. I don't expect you to remember the details. You can always go and pick them up when needed. Some of you will remember, which is very good, very nice. But the other details, others can pick up the details when it is necessary. You'll have a chance to refresh your memories sometime later during the course also on the measurement methodologies. So we looked at fluorescence in some detail because we use them in the lab. We looked at other methods just in passing. There are many methods, many quantitative methods just in passing. And then we looked at EPR principles in some detail and finished up with biomarkers. So the first 3 chapters are pretty much done. I'm going to ask you to watch a reasonably long video. I think it's about 8-9 minutes long. Good to watch it here, which is there on your, which is the last video. It's a YouTube video on the 3rd chapter, the last video, the 3rd chapter. Summary. Okay. And this is a summary of the first of the information that we have covered so far. It's a very nice summary, well done by osmosis. Earlier, I think we needed I needed an account on osmosis to watch it. Then I found a YouTube source, so put it up. Please watch it. I'll also run it once and then continue with the next chapter after you finish. It gives you an overall idea of reactive species, antioxidants, and so on. Nicely done. In your free time, you could also watch that in vivo EPR. That I guess it got missed out here or something. That's okay. That tells you how to use EPR for whole animals and things like that. It's been done. Most of the time, we use it in for samples, thin EPR tubes, a few ml at a time, kind of a thing. But you could do whole animals with EPR. Whenever you get the time, you could watch that. The video before this. I don't think I assigned it during the class, right? Probably not. Okay, that's okay. That's a nice video. It's a little old, but it's a nice video. Free radical cause? I didn't quite catch the word. Free cause what? Non-alcoholic fatty liver disease. Yeah, those diseases, they are fully fully implicated. Lots of diseases, by the way, and it gives you the basis for that. Metabolic model, yeah. Oh, okay, good. Okay. Certainly, yeah. And no, I mean, it's already published anyway. Everybody can use it, right? And I'm glad he wants to continue in this work, which is very good. The history is something like this. I don't think I told you the history of this particular work, right? It took 14 years to publish that reactive species module. Um, started the work sometime in 2009, I think. I had finished my term as the head in 2008. Yeah, 2008 itself, towards the thing. And I wanted to do something which is fundamental enough and which is usable enough and so on and so forth. We've done work on various different aspects. I'm very happy with the work done. Okay. If I think of the work done even about 30 years ago, it brings a smile to my face, which is very nice. I'm very happy with the work. I never compromised on that. And I never wanted to do incremental work. I wanted to do work that appealed to me. So that absolutely no compromises. Happy with that. But this is taking it a step further, more fundamental, more this thing, and so on and so forth. And always thinking about whether people can figure out how reactive species affects their system in some way, and so on and so forth. At that point in time, what was popular was a set of differential equations representing metabolic aspects through a set of differential equations, dynamic modeling. And so we tried that approach, kinetic equations, and so on. I thought we could, I mean, I knew the difficulty. I knew it won't scale because I was not too sure whether the constants were available. You need the rate constants for that. You get the concentration variations with time, but you need the rate constants, obviously. That's the way the equations are. So I thought we could manage some way and went into it. I set aside 5 years for that. Started in 2009, set aside 5 years. And I didn't give it to a PhD student. I knew it didn't have an end, so I didn't want to risk it on a PhD student because the thesis will be in trouble if it doesn't work. I did a good thing. When I cannot see the end, I don't give it to PhD students. So then it was dual degree students. Dual degree students, fine. They write their report, something comes out of it, and they get their degrees. And so they kept contributing, each one part, and so on and so forth. They went on for 5 years. And then I realized we're nowhere near completion. Some small things we could do, the constants were not available. Search. No, nothing is available. I knew some databases were available. That was my background confidence, but that was not enough. For the NIST database has a huge list of reactions and reaction rate constants, but that was not enough. And so then I joined hands with Raghu, who's currently the Dean, International Affairs. And he is good in math and so on and so forth. So we are looking at means by which we could predict the constants, and then check whether it is really working. At least we'll have some confidence in doing this. So that went on for some time, 2 more years. But the end of sixth year, I kind of had to accept that it's not going to scale. It'll work. It'll certainly work in a small level, but it's not going to scale to represent the entire set of reactions. By that time, Swagatika joined. Swagatika Sahu joined as an inspired. She's not here anymore. She was in chemical engineering. We were all in the same group working together on common problems. Nirav also joined the same group. He was not a faculty then. He was also an Inspire faculty, not a permanent faculty then. And he became a permanent faculty in 2018 or 2019 or something like that. And then we all worked on this. In fact, the initial work that Subhashri did towards her master's thesis, she didn't take a master's, she shifted to a PhD, was guided predominantly by, it was the problem that I had formulated, but it was guided predominantly by Nirav and so on and so forth. So he has been in the group. When we were talking, I think a year into the work together or 2 years into the work together, sometime in 2017 or something like that, I asked in the group, can we do this? If it's a brute force thing, can we write these reactions one after another and try to integrate it in some way with the metabolic model? It is my idea. And then Swagati immediately said yes, and there is a need for it, and so on and so forth. She could see the need immediately because she's a complete systems biologist. She's made all her contributions, nature biotech and things like that, papers in systems biology aspect. She has worked with some of the top people in the field, Ines Thiele and so on and so forth. Ines Thiele worked with Paulson, That's the lineage that she has. So she said, fine. Then I was confident, and then we got into it. I said, 2 years done. We have this NIST database. We bring everything together. Another 5 years. But at the end of that, Prerna had finished. So I had asked Prerna to put all these things together. Let us see where it goes. We put all these things together from a different angle. That was not very acceptable to we. But there is an archive, bioarchive paper on that. But that angle, which was drug discovery angle, was not very, did not appeal to the reviewers and so on. So then we realized that just the module itself is good enough as long as we give some example and things like that. Subhashri was working on a few cancers at that time, modeling. So, and she was interested. It kind of organically happened. Nirav was always there. He was the co-guide at that time. All came together, and then she got into it. She worked on it for 2 years. She is into systems biology completely. She knows the ins and outs. She worked on it like crazy, and then Herculean effort, and then she integrated the whole thing, and something came out of it. So Subhashri, then Prerna, who's the other PhD student who had earlier worked on it, and others among the DD and project students who had contributed to this significantly were authors. The rest were acknowledged. Everybody who worked on it has been acknowledged in that paper, and that's how it came. So it was quite an effort, which I could afford because I was senior enough and I didn't need quick papers and so on and so forth. Then, essentially, if you need to contribute something big, you need time. That's what it is. So that's how it came about. So it's all a common thing. And now Nirav is on paper, I am the guide, and Nirav is the co-guide for Subhashri. But in practice, it's the other way around. That's because my view on systems, on this approach, the earlier even flux sampling was not there. Flux sampling I'm fine with because at least there's certain acceptance that it is a stochastic aspect, and you're trying to get an average value and so on and so forth. Earlier parts, they would just put in some numbers and say, this is it. What's the basis for those numbers? Well, there's a certain reason for doing that, just to get an idea. But that was not very appealing to me. So I never got into systems biology. I got into it only for reactive species. And because of that, I did other things also. We have papers, excuse me, we have a lot of papers, not a lot, we have a few papers on systems biology aspect to various different things. But that was because of the need for putting in a module for reactive species, nothing else. And that's why I tried to get out of it. The recent dual degree projects I gave totally different projects based on dynamic modeling, but it kind of veered towards systems biology for a more complete approach. Students came and said, why don't we do this? And then I said, if it's coming on naturally, who am I to stop it? And it's a more complete approach, certainly. Only thing is that it is in a developmental phase, so the confidence that's associated with those numbers are different. Now it's okay. Now I think it's still acceptable to me, but the approach is a little too brute force. personal view. But we have made contributions there also. Any other questions, comments? Another 5 minutes. But so it's what I was trying to say was that it's we all have contributed significantly each to that. Whoever the idea was and so on. So the final product is this. I'm very glad that it is going forward. Which means, yeah, there's a lot of interest. As soon as we published that paper, there was a lot of interest. I haven't seen that amount of interest for that kind of work in the recent times. There are the earlier work that's, I guess, Subhashri's luck. The earlier work that Subhashri did was on biocementation. She did modeling on that. And when she did that, somehow the world was so interested in that. So many, queries, so many requests for popular articles and so on. So I wrote that wave also. I never worked on biocementation earlier. Got into it only because of Subhashri and the Curtin University people we are working with. They were looking at biocementation. That's how we got into it. Raja worked on biocementation. He was a joint student. But I was always clear that there has to be some reactive species angle. You will find a reactive species angle in many different things. So I'm very confident about that. So when the earlier student who Herald went to Curtin to work with Tushar there and me here. It was initiated by Tushar, and then he said, "We'll work out something together." I told Tushar was my old student in IIT Bombay. I told Tushar, "You work out. I'm sure I'll figure out a reactive species angle to it, and then we'll finish." That's what happened. He worked out something on anaerobic digestion completely. So this guy's Herald's thesis was on anaerobic digestion, but there was enough reactive species. So, 3 papers, 2 to 3 papers. Okay. Any other comments? If not, I'll just start out. It's criminal to waste 10 minutes, so I'll at least take 5 minutes, and then before it gets too overpowering, I'll let you off today.